All right, good morning, everyone. Today we're taking on hypothesis testing, which is pretty fun, and it's our last topic, our last big topic. So we're very close to the end now. Today is a very important lecture. Okay, so there are two common types of statistical inference. We've already covered one. We've covered confidence intervals. So we use a confidence interval when our goal is to make a prediction or an estimation about a larger population and its parameter. Our second one, where we're diving into today, is hypothesis testing. So a statistical hypothesis is an assumption about a population parameter. This assumption may or may not be true. Hypothesis testing refers to the formal procedures used by statisticians to either reject or fail to reject statistical hypotheses. So I have one big example that I'm going to use throughout my lecture today. So we have a 2016 report from U.S. Consumer Product Safety Commission claiming that at least 90% of all American homes have at least one smoke detector. Okay, so if that seems important, I'm going to underline it. A city's fire department has been running a public safety campaign about smoke detectors with posters, billboards, and ads on radio and TV and in the newspaper. The city wonders if this effort has raised the local level above the 90% national rate. So we're seeing if all of these grand efforts have raised it. Okay, building inspectors visit 400 randomly selected homes and find that 376 have smoke detectors. Is this strong evidence that the local rate is higher than the national rate? Okay, so we have 4 steps to conducting a proper hypothesis test. So first up, we have to write our hypothesis. Okay, so A, we start with the null hypothesis. So the null hypothesis, we write an H here with a sub O like that. So when I read it, there's actually a few different ways we could read it. We could read it as, let's write read as H naught. Right? That's how you would spell it, but it's like a naught, like a K-N-O-T naught. H naught, H O, or H null. So whenever we see that H with that little sub O, right, it reads as H naught, H O, or H null. All of those are fine. This is a statement about the population parameter. So in this case, going back to what we already know about smoke detectors, right? We know that 90% of American homes, at least 90% of American homes, have at least one smoke detector, right? That's what we're told in the setup. All right. It is the skeptical claim that nothing interesting has happened, nothing's changed, there's nothing unusual about the results. So we're essentially saying, okay, maintains the status quo. We're saying business as usual. So a good analogy that we often use with hypothesis testing is we just go back to the legal system. And we remind you that if I try to relate this to the legal system, the null hypothesis would be that the defendant is innocent, right? That he or she is presumed innocent until we prove otherwise, right? We have the burden of proving them guilty. So we write this then as HO or H naught. We're saying everything is stayed the same. We are saying that the parameter is 0.9. Right? 90% of American homes have at least one smoke detector. So here, just want to make sure I stress, this is what we already know about smoke detectors. So again, our null hypothesis, always about the population parameter, right? It's maintaining the status quo. What is it that we already know? We know that 90% of American homes have at least one smoke detector. Okay, your null hypothesis will always be P equals something right there. Then we have our alternative hypothesis. So this is the statement about what we believe is happening if we reject the null hypothesis. It's saying that there's something different than our null hypothesis that's occurring. So our alternative hypothesis is just an H with a sub A like that. And when I write it, it could be two different ways. So it could be that P is greater than 0.9, but it could also be that P is less than 0.9. We're saying, okay, well, maybe there's a shift. Maybe it's more than 90% of American homes that have at least one smoke detector, but maybe it's less than 90%. Maybe we recognize that there is a shift in one direction. So we call this one-tailed. Okay, and since I'm already here, I'm just going to show you what that visualization would look like. So for one-tailed, we're interested in spotting a change from the null hypothesis in only one direction, higher or lower. So I'm going to put my p-value right here, 0.9, right? That's what my null hypothesis says, right? 0.9. So let's say that I came up with a statistic that was, say it was like 0.85, right? This is what I'm checking for over here, that lower left-hand tail. This would be a left-tailed test. And it would be saying that the alternative hypothesis is that P is less than 0.9, right? We believe that the percent is lower than 90%. Okay, so again, this is just an example of a one-tailed, specifically left-tailed test where the alternative hypothesis is that P is less than 0.9. We believe that the percentage of people with smoke detectors in their homes is lower than 90. Okay, but it could be the other direction too, right? It could be that we believe that it's increased. And that's really what this problem is about, because it's saying, have all of these public safety efforts increased the amount of smoke detectors in American homes? So we could come up with a statistic of, say, 0.95, for example, right? And we're looking at that outcome instead. So this would be a right-tailed test. We'd be saying that the alternative hypothesis is that P is actually more than 0.9. We believe that the percent is higher than 90%. Okay, so again, just going back to why our alternative hypothesis would be one-tailed, we're saying that we see that there's a shift, but our shift is only in one direction. So in this instance with smoke detectors, we're saying, do we believe that there's been a change that actually less than 90% of homes have smoke detectors? Or have we seen a shift here where we see more than 90% have smoke detectors? Okay. We also have the potential of having a two-tailed test. So if it's a two-tailed test, H sub A, right, the alternative hypothesis would be that P is simply not 0.9. So this would be two-tailed. Okay, and then here to visualize that, here is the p-value that we came up with. And we're saying, well, it just looks like the city may have a different percent than the national average, but it's not implying a directionality. It could be either higher or lower. We're just saying, you know, it looks like that percent has changed. It's not 90%, but it could be lower, could be higher. So it could be, for example, I get, 0.85, 0.95 is my statistics, like here and here. So again, this is a two-tailed test. We're saying that our alternative hypothesis is that, well, it's just not 0.9, right? But we're not indicating higher or lower. So this would be like, we believe the city has a different percentage than the US average of 90%. Okay, and what has to be super clear here that makes it stand apart from the one-tailed test is that it could be lower or higher, right? There's no indication of the directionality. So it could be lower or higher. Okay, so for this first day of hypothesis testing, we're sticking in the one-tailed test. I want to really drill that in first, and then we will move on to the two-tailed tests. Okay, so again, the situation that we're dealing with right now, we're looking at smoke detectors, right? We know that our null hypothesis is P equals 0.9. Right, that's what we already know about smoke detectors, that at least 90% of American homes have at least one smoke detector. And then we're looking at this situation here in our context, because we're looking at, have these local efforts to bring about, safety campaigns with posters, billboards, ads, right? Has that increased? Do we have evidence that the local rate is higher than the national rate? So ultimately, I already have my eye on what we're solving for. Our situation will look like this one right here. All right, flip it to the back. Okay, so we've already done our null and alternative hypotheses. So now we choose a model. What kind of test is needed? Okay, if I'm being formal in my language, we're saying we're going to do a one proportion z-test. Okay, and then we have to run through our conditions. And I just want to point out that they are exactly the same conditions that we saw for confidence intervals, right? So we need randomization. We want our data to come from a random sample from the population of interest. We want it to do an excellent job of representing all the types of individuals in our larger population. Okay, independence, right? Our data values should not impact each other. 10% condition, right? Our sample size should be less than 10% of the population. And then success failure, we must expect at least 10 successes and at least 10 failures. So here, just a reminder that this is really the same conditions as with confidence intervals. Okay, so then when we calculate next, we have to figure out, well, what is our statistic? So we know our statistic is a p hat. We're looking at our observed successes. Okay, over our sample size. Okay, so in our problem, for example, so back to the smoke detectors, we were told that 376 households did have a smoke detector in this town or city, and then we had a sample size of 400. Okay, so we're looking at our observed successes over the sample size, and we're getting a statistic of 0.94. So the statistic that we came up with is that, well, 94% of these people that were randomly picked from this smaller city, we saw that 94% of them had a smoke detector installed in their home, at least one. All right, so then we would make a sketch, mark the hypothesized parameter, the sample statistic or statistics, shade the appropriate tail or tails. And then we calculate the value under the test statistic. Find the p-value. So this is where it gets a little sneaky because we get a lot of p's, right? We have the p for parameter, we have the p-hat for statistic, and now we have the p-value. So think of this as a probability value. That is what we're calculating. The p-value is a probability. It's the probability that the observed statistic would occur if the null hypothesis were correct. This is the area under the curve for the specified values. So you're going to see me walk through that in just a moment. So let me slide it up, and I'm going to start that with you right here, just putting it all together, and then I'm going to come back to step 4 in just a moment. So here, again, context. We're looking at a 2016 report from U.S. Consumer Product Safety, and they're claiming, well, at least 90% of all American households have at least one smoke detector. A city's fire department has been running a public safety campaign about smoke detectors with posters, billboards, ads on the radio and TV, and in the newspaper. The city wonders if this effort has raised the local level above the 90% national rate. Building inspectors visit 400 randomly selected homes and find that 376 have smoke detectors. Is this strong evidence that the local rate is higher than the national rate? Use an alpha level of 0.05 as your significance level. We're going to deal with this part in just a moment. So step 1, the hypotheses. So again, we already did these. The null, H naught, H-O, right? Lots of ways of saying it, is that P equals 0.9. We're saying our null hypothesis is business as usual. That rate is the same. 90% of households have smoke detectors. Okay, what is our alternative that we are arguing? So our alternative is that that figure has gotten higher than 90%, right? We're saying, well, with all of these amazing efforts, right, we're saying, well, let's see if the local rate is higher than the national rate. Let's see if it has increased, up or tail. Okay, walking through our criteria, do we have randomization? We sure do, right? So big check right there. So we know that it says random, usually says SRS. It gives us some sort of language to tell us that it's random. Okay, do we have independence? Check, right? We are assuming that if we're using a random method that one outcome is not going to impact another. Okay, for 3, our 10% condition, I'm going to say check, right? I would assume that 400 individuals are less than 10% of this city's population. Okay, and then for the success failure, do we have enough successes? Do we have enough failures so that this would look relatively normal? We have to check, is NP greater than or equal to 10? How about NQ? So here I'm taking 400 and multiplying by 0.9. I get 360, so yes. Here I take 400 and I multiply by 0.1 and I get 40, so yes. We have at least 10 successes, at least 10 failures. All right, so now we're calculating the p-value. So calculating the p-value, and again, here we are among many p's. So the p-value is saying, well, what's the probability that this would play out? So here I'm going to go ahead and just write that my p equals, right, this is my parameter, p equals 0.9, right? And then we put that right smack right here because that would be the mean of my distribution. What is my statistic that I'm showing? So here we're looking at the 376 over 400 individuals from our city that have a smoke detector, and we get a 0.94. Okay, I don't know exactly where that's going to fall here. I'm just going to put 0.94 right about here and mark a little notch for it. Okay, again, I'm just trying to visualize what I'm solving for. Okay, so here what I'm trying to solve for is that one tail, that upper tail. I'm looking to see, well, what would be the probability of me getting an outcome of 94% or more, right? That's what I'm going to solve for in just a moment. Okay, I need my standard deviation. So my standard deviation would be the P times the Q over the N. So 0.9 times 0.1 over 400. So P times Q over the N, square root, and I get 0.015. Okay, so I know my parameter, and that will be my mean right here. I know my statistic, right, from my city, the 94%, I mark that here. And then we're looking for evidence that the rate is higher. So I'm looking at that upper tail, that's what I'm solving for. And I just calculated my standard deviation. So now when I'm trying to solve for this probability value, this outcome occurring, right, I go back to my normal CDF, my lower boundary, 0.94, my upper boundary, well, that's my infinity, so I need a placeholder, something that is really big, so I usually use 9,999. Even if I use 99, it would be fine. The idea is a placeholder for infinity. So 9999 is what I'm going to use, so lower, upper, and then here my mean, 0.9, right, 0.9, and the standard deviation, 0.015. So again, here is my statistic that I obtained, right? That's my lower marker up to infinity. Here's my mean, here's my standard deviation. So when I crunch that, grab my calculator. Here I'm going to get, let's see, I have 0.94, 9,999. 0.9 and 0.015, just like that. So I'm going to get 0.0038 as my probability. So my p-value, my probability value, is about 0.0038. Okay, so I've calculated. Now I just have to figure out what does that actually mean, right? So that's where I'm going to drag it back to here, that part 4, stating your conclusion. So we need to state a decision about the null hypothesis. We're either going to reject it, or we're going to fail to reject it. Okay. So we're going to link our p-value. Remember, we think of that as a probability value. Since we have so many p's, p-value means probability value. So we link our p-value to our decision and we include some context. So we always also have an alpha level. We've already seen that our problem is saying our alpha level is 0.05. So we are always given an alpha level. Let me add this detail. So your p-value, when we say we have something low or high, its threshold depends on the alpha level. Okay, so right here, that symbol is alpha. Okay, so our p-value, whether we're saying that it's low or high, which in turn allows us to reject or fail to reject the null hypothesis, right? It really depends on the alpha level of significance that we set. So in our situation down here, we're saying we're going to use a 0.05, so 5% as our significance level. So if we see a p-value that's low, so here low means lower than the alpha level. So if I see something low, lower than the 0.05, and in this case I get something really low, a probability of 0.0001 would be very unusual, especially if I set my bar at 0.05 as my alpha level. So my p level is low, lower than the alpha level that we set, and then we're going to reject the null hypothesis. That would mean that we're seeing strong evidence that more than 90% of homes in this city have smoke detectors. We're saying this outcome is so low that we don't think the status quo is being maintained. We think there has been a change for the better here, that more than 90% of homes have smoke detectors. If the p-value, probability value, is high, again, higher than that threshold we set at 0.05, our alpha significance level. So here we're saying, for example, 0.15. Then we would fail to reject the null hypothesis. We're saying that outcome, not so unusual. We are not seeing strong evidence that something has changed, that more than 90% of homes in the city have smoke detectors. So let's go back and let's answer our question that was posed here. So we're saying, okay, do we see strong evidence that the local rate is higher than the national rate? Here is our alpha level, our level of significance. So again, right here, that symbol is alpha. And here we should know that we're going to reject if it's lower than the threshold. So if lower than 0.05. So let's go back to our p level. Our p-value here, p-value is 0.0038, right? That's our probability for this outcome. So we're going to say here in summary, with a low p-value, probability value of 0.0038, right? So it's low, it's well below that threshold. We reject the null hypothesis. We think this likelihood shows that it's so unusual for this to play out. We reject the null hypothesis. We think there's evidence that something has changed. So we finish up with, there is strong evidence. We believe there's strong evidence. And we add our context. More than 90% of homes in the city have smoke detectors. Okay, there we go. So, in summary, right, we start with our hypotheses. We always have a null. There will always be an equal sign here. Our alternative, right now we're looking at one tail, so we'd see something p is greater than or less than whatever we stated here in our null hypothesis. We're saying we think something has changed. It's either increased or decreased when it's a one-tailed test. We check our assumptions, the same four that we saw for confidence intervals. We now calculate, this is the same as how we did it for a sampling distribution for proportions. This skill has not changed. We've just added context to it. So a p-value is a probability value, right? It's the likelihood that this scenario would play out. So we're saying here is our null hypothesis that 90% have smoke detectors, at least. Okay, this is the statistic that we came up with. This is right here. This is our standard deviation based on our p-value right here. The p equals 0.9. Okay, so then over here, right at my mean, that is the parameter. That is my null hypothesis. I mark where my statistic falls, right? I remember, is it saying that something has increased or decreased right now? Since we're talking about a one-tailed test, we're looking at has something increased over a period of time. And then we just solve it just like we did with our normal distributions. We're finding the area underneath the curve, right, which tells us the probability of this outcome playing out. So when we type it in, we're going statistic to infinity. Here's the mean, here's the standard deviation. So my probability value, my p-value, I always write it like that to remind myself this is probability, is 0.0038. That is so unusual. That is so low. That is so rare to play out. We're saying in summary that this value is so low, that outcome is so unusual, we don't think that the status quo has been maintained. So we reject the null hypothesis, and that means that we are seeing strong evidence that there has been a shift. More than 90% of homes in this city have smoke detectors. All right, big, important lesson today. I hope all of that made sense. Ask me questions as they arise. Have a good rest of your day.